So we have learned the basis functions. So we know there's two types of basis functions. One is a Fourier basis function if underlying function is periodic. The other is when the function is non-periodic, we will use B-spline basis functions. So after we decided the basis functions, the next step we need to do is try to estimate the coefficients to these basic functions to get the function itself. Okay, so now let's learn how we can estimate the coefficient to the basic functions. So here is the model we use. Suppose we have some observations y1 to yn at this time point t1 to tn. And suppose we have yi is equal to a function f over ti plus some random error or measurement error epsilon I. So here we assume that this random error epsilon I follows a normal distribution with mean 0 and variance sigma square. And we assume that this measurement error epsilon I are independent. So here we don't have any parametric assumption on the f of t. So now the question is how can we estimate f of t from the noisy and discrete data? So the main technique we use is using this basis expansion. So basically we will write down this function f of t as a linear combination of the basis functions. Okay, so suppose here we have capital K number of basis functions and phi 1 to phi j, sorry, this should be j, capital J. Okay, so we have phi 1 to phi j are the basis functions, and C1 to Cj are the coefficient to the basis functions. So the first question to decide the basic functions, we have no, right? So for non-periodic, for periodic function, we were using Fourier basis function. For non-periodic function, we were using B-splines, right? And we were typically using cubic B-splines. We sort of order equal to 4, and then we decided the number of nodes, okay? The second question is how can we decide the coefficient to the basis functions? Okay, so I already covered this. Sorry. So how can we estimate these basis coefficients, Cj? So we were using least squares estimation. So here we try to minimize the sum of square errors yi to the FTI. So we have this sum square error, and so we can write down this sum square error as a function of the basis coefficient C here, right? So this is just actually just a linear regression, and if we write down this sum square error as some matrix form, you can write down this as y minus phi c transpose times y minus phi c. So here, capital Phi is an n by j matrix. We call it basis matrix. So basically here, this capital Phi has n rows and j column. So in each column is one basis function at this n time point. Okay, and so then based on the ordinary least square estimation, we can have C hat equal to phi transpose phi inverse phi transpose y. After we get these basis coefficients, our estimate for the function f of t will be just C transpose times phi of t, right? Yes. Any questions? Okay. So after we get the get this get this f hat of t, we can also look at the value of f hat of t at the observation time points. So basically, y hat here is the fitted value at the observation points. So y hat here is phi times c hat. Okay, so if we put the formula c hat here, and we can get this y hat equal to phi times phi transpose phi inverse phi transpose y. Okay, and so everything in front of y, we call it as a big matrix called S. S is called a smoothing matrix. Okay, so basically S is equal to phi times phi transpose phi inverse phi transpose. Okay, so the reason we call it S as a smoothing matrix is because basically Y is the original observed noisy data, right? So then if we're using S times Y, basically S transformed the original data to the fitted smooth data Y hat, right? Therefore, we call it S as the smoothing matrix. Actually, this S is very important in this smoothing framework. We will learn this later on. The reason is because you can show that if you take the trace of the S, you will figure out the trace of S here will be equal to, what's the trace of S here? Can you see? For the trace of the S, we know the matrix multiplication cannot be changed the order, right? But if you take the trace, then you can change the order of the multiplication. Therefore, if you take the trace of these complicated 4 terms, then you can take the phi to this phi to the right side, and then suddenly this will be cancelled out, become an identity matrix. And the order of the identity matrix will be J, right? Therefore, the trace of the identity matrix is equal to J, right? Yes. Yeah. So you can see here, S actually is equal, the trace of S is equal to J. J is a number basis function. In other words, the trace of S is equal to the number basis function and equal to the number of coefficients, right? Therefore, so basically, the J here is the number of parameters in this model, right? So therefore, the trace of S is the number of parameters in the model. So later on, when we including the roughness penalty term, then it is hard to determine the number of basic functions. Hard to determine the number of effective parameters. In that case, we will just use the trace of S as the number of effective parameters. So we will talk about this later on. So that just want to give you ideas. This S is very important for us to decide the number of parameters in the model if we don't know. Okay, so this is how we estimate the basis coefficients. So one question we haven't touched on is that we know the type of basis function we use, right? But we haven't talked about how to choose the number of basis functions, which is also very important, right? For either Fourier basis functions or the B-spline basis functions, So for B-spline basic function, we know that we will use a cubic B-spline basic function for most applications, but we have to decide how many nodes to use, right? In other words, how many basic functions we should use. Okay, so this is kind of what we already often have to doing some balance. So if we choose a small number of basic functions, then the function will have a small number of coefficients, and the function will become have little flexibility. If you're using a large number of basic functions, you increase the flexibility of the basic function, but it may overfit the data, right? We know that if we overfit the data, the prediction will not be good, right? Yes. Therefore, we have to choose the number of basic functions carefully. So here, to give you one examples, for the Vancouver, so this is to show the delay precipitation amount in Vancouver over 1 year. Okay, so we know in Vancouver we have a lot of rains in the winter, right? So we have a lot of rains in the winter, and generally we have less rains in the summer. So, this is the discrete delay precipitation data in the red circles. So here, if we choose 3 Fourier basic functions, this is how the fit looks like. Looks pretty good, right? Yes, I think it's pretty smooth and also capture the general trend pretty well, right? And if we try 5, I will see even better, right? It kind of will capture this left part. I think is better than the previous one. Previous one kind of will like level off here, but actually we know in January we have a lot of rains, right? Yes. So if we have 7, it's still pretty good, right? And if we have 13, we will suddenly see a lot of small wiggles here, right? Yes, I will see this 13 when using 13 Fourier basic functions. This function become not smooth enough anymore, right? So therefore, for this case, if we just look at the graph here, I will not recommend a 13 Fourier basic function because we have suddenly the fitted function has these local wiggle points, right? You have 19, we even have more wiggle points, okay? And you have 25, we clearly overfit the data, okay? We can try them all, and I think generally we overfit the data, okay? So if we're using 365 Fourier basic function, because we only have 365 data points, basically we are able to go through each data point, okay? So the fitted error will be 0, okay? But we know this is definitely overfit, right? Okay. Yes. Any questions? Is this good? Okay. So this is just to give you one examples. When we change the number of basic functions, the fit can be very different, right? Okay. So here, when we choosing the number basic function, we have to do a trade-off. So if we use too many basic functions, we will overfit the data, and we may follow the error of the measurement, right? And if you have too few basic functions, we may lose the flexibility to capture interesting features of the curve. So this is a theme as the trade-off between bias and variance. So here, just to give you the impression for the bias. So the bias is ft minus ft hat, and the variance is expectation of ft hat minus expectation of ft hat square. So if we have too many basis functions, we will have a small bias but a large variance. If we have too few basis functions, we will have a small bias, a large bias but a small variance. So we know that the gold standard is to try to minimize the mean square error, right? So the mean square error is equal to the square of the bias plus the variance. So here we have the pointwise mean square error at each time point. If we just want to summarize over the whole intervals, we can look at the integral of this mean square error. So here it just give you one simulation study. So basically here we will first fit the Vancouver precipitation by B-splines, and we can get the estimated f of t, and then we treat this f of t as the true curve, okay? And then we will calculate the fitted error yi minus f of t, and then we can create the new data by randomly resampling this error epsilon I, right? Yes. And after we get this randomly sampled error epsilon I star, we can add this randomly error epsilon I star to the true curve f of t, and we can get the simulated data yi. And then we can fit this data by Fourier basis functions, and we can get the estimated curve, right? We can do this process for 1,000 times and calculate the bias and the variance for this estimation. So here, this is to show the bias, the change of the bias, variance, and mean square error change over the number of basis functions. So as we mentioned that when the number of basis function is increasing, the bias is decreasing, right? The red line is the bias, is decreasing, and the variance is increasing. And so the mean square error is decreasing at the beginning, and then it increases again, right? Okay, so if you look at this curve, what's the optimal number of basis functions we choose? Around 13, right? No, around 13, yes. The minimum of the mean square error, right? Yes. Okay, so this is we will choose the same the optimal number basis function that minimize the mean square error is 13, right? Okay, so this is a simulation study, but in reality, we cannot. We don't know the true function, right? So in reality, if we don't know the true function, how can we choose the number basis function? We can use in cross-validation. So what we can do is we can try to randomly select one data points, ti, yi, right? We remove this point, and we will estimate the function using the remaining data, right? And we denote this as f hat sub minus I of t, okay? Because this is kind of after remove the i's observation, and then we can measure how the fit of this function to the yi, okay? Because when we estimate this f hat sub minus I, we don't using the i's observation, right? So therefore, we can treat this error as the prediction error, right? Yes. Okay. So therefore, for each of these data points, we can do this, and we can find this prediction error, and we do the sum squares, and so this will be called ordinary cross-validation scores. Okay, so therefore we try to find the number basis function that minimize these cross-validation scores. Okay, and suppose if we're using a linear smooth function, linear smoother, like the model we use when we're using f equal to the linear combination of basis functions, you can derive that this ordinary cross-validation scores is also equal, can be written like this. Okay, so here the f hat is to use all the data to estimate f hat. Okay, so in other words, you can show that if we use this formula, you don't need to do this cross-validation for each time point, right? You can just fit the data for the whole data, get the f hat, and you also get the smooth matrix S, and get the diagonal element in the smooth matrix SII, and then you can calculate the cross-validation scores. Actually, you don't have to do the cross-validation. Okay, so this is very handy. Okay, so this is the cross-validation curve for the Vancouver precipitation data. I just show you, and so you can see here basically these cross-validations. It seems to minimize when number basis function equal to 21, right? But we will not recommend 21. We just before we have doing the simulation study, we know that the optimal number basis function is 13, right? You can see here basically 13 is the first point when the cross-validation scores is minimized, kind of a local minimizer, right? Yes. Yeah, this actually is generally true for many applications. So the cross-validations, we don't recommend to choose the number basis functions that minimize the cross-validation scores. We often choosing we call it elbow point. So we choose the number basis functions that the cross-validation firstly reach the minimum. Okay, so in this case is equal to 13. Okay, so in other words, we want to choose them as small number basis function as possible. Okay, therefore, if we just have these cross-validation curves, we recommend to choose 13 number basis functions. Okay. Any questions? Okay. So after we get this decided number basis functions, we can do the least squared fit, right? We can fit the curve, and then we can also estimate. Remember, in our models, we assume the measurement error follows the normal distribution with mean 0 and a variance sigma square, right? So we can estimate the sigma square by using the sum square of the fitted error divided by n minus j. J here is number of basis functions. Is also number of parameters, right? Number of coefficients. So this is unbiased estimate for sigma square. So after we get the estimation for sigma square, we can find out the variance of the fitted curve. The reason is because we know the vector of the basis function, basis coefficient C, is equal to matrix C times Y. So capital C is equal to this. It's basically the matrix, right? So then we know that the variance of the vector C is equal to sigma squared times C transpose. And you can, doing the matrix multiplication, you can show that C times C transpose actually is equal to phi transpose phi inverse. Okay, and also you can calculate the variance of f hat. Okay, so the variance of f hat is again you can, because f hat is equal to phi of t times c, right? C hat, you can calculate the sample variance of f hat. And also you can get the variance covariance matrix for the fitted value f hat. After you get the variance covariance matrix of f hat, the fitted value, you can find out the confidence interval for the fitted curve. So basically the confidence interval for the fitted curve f of t will be f hat plus minus 2 times square root of the variance of f hat of t. Okay. So here is the examples. So this is the estimation for the precipitation curves, and the dashed line is the confidence intervals when we're using certain Fourier basis functions. So here is a summary of the procedure. So basically, we will fit a smooth curve as a linear combination of the basis function. We will estimate the coefficients by the least squares. So we will using the cross-validation to choose the number of basis functions. And we can calculate the confidence interval of the fitted curve by using this matrix calculation. So in the next lecture, we will learn a better way to control the bias and the variance. In other words, if we have a large number of basis functions, how can we control the bias and the variance trade-off? So we will learn this in our next lecture. Okay, so any questions?
So can you go to the slides about the variance?
Sorry?
The variance of the estimated,
This one?
No, the estimated variance of so yeah, this one.
Yes.
So is there any property about this variance estimator?
Any property of the variance estimator?
Yeah, so let's say the variance of C. Is that like a consistent estimator? Or is it conditional on the number of basis functions you are using?
Yeah, I think this will be a consistent estimator because yeah, I think there's some asymptotic properties for this fit. Yeah.